Frames and machines. By the end of this section, you should be able to recognize and identify a problem as a frames and machines type problem versus being a truss problem like we saw in the previous section. You should be able to properly create the multiple free body diagrams for these multi-body systems and correctly place internal and external forces into the free body diagram. From these free body diagrams, you should be able to create a system of linear equations and solve for the external and the internal reactions in the system. And you should be able to identify two force members in the system by inspection. So let's begin by seeing what is a frames and machines type of problem. A frame or a machine is going to be a structure made up of multiple members that are linked together in some manner. It could be pins, or they're pegged together, or hinged together, but there's multiple members connected in some way. Now, really we just saw this when we were looking at truss problems, and a truss is basically a very specific version of a frames and machines problem, or conversely, frames and machines is a generalization of truss problems. Like we saw with trusses, multiple members were connected together to form our entire system. However, trusses were a specific version of frames and machines problem because in the truss, every member was a two-force member, which we'll talk about in a little bit what that is going to mean. And in a truss, all the members had to be connected together with pins. And furthermore, we saw that we could not have any forces acting along the span of any of the members. And all of those requirements for something to be a truss are now relaxed in how we are going to be more generally analyzing frames and machines type of problems. We're going to see that the forces need not be directed along the length of the member, in that not every member, possibly no members in our frame or machine, are going to be a two-force member. Almost always we're going to see that our systems are statically indeterminate when we are dealing with frames and machines type of problems. So rarely in these problems will the external free body diagram give us enough equations to be able to solve for the support reactions or those external reactions in the system. So these differences and slight complications from what we saw in a truss system are going to necessitate a little bit broader of a procedure in order to solve for all of the internal supports, all the external supports in our frames and machines problems. So how we go about solving for all of these unknowns that we're going to be generating in these systems. Well, since most of the time we're going to have these statically indeterminate systems, I'm going to recommend always skipping the external free body diagram and jumping right to separating all the members of your frames and machines into their individual parts, and then individually draw each of their free body diagrams. We want to give each free body diagram a label of some sort so that when we go to write our equilibrium equations, we know which sum of forces it's coming from, which sum of moments it's coming from, which diagram do they pertain to. Any reactions, external or internal, that we're interested in finding must appear somewhere in one of the free body diagrams that we draw. As a time-saving measure, before we start drawing free body diagrams and taking our system apart, it might be helpful to identify any two-force members that are in our system. Remember, a two-force member is what every member in a truss was, and it's going to be a member whose force is directed along the longitude of it. But in the next subsection, we'll talk about how do we identify and use two-force members in more detail. And if we have more than two members meeting at a junction, we're going to need to draw the junction itself, typically a pin. But we'll talk about that in the last subsection of this topic. So every individual member is going to get its own free body diagram in this first step. Some of these free body diagrams are going to include external reactions. Some of them will include only internal reactions. On the free body diagrams, we need to draw all of the applied forces and the moments. So if we have these external forces and moments or couples being applied on a member, it's going to get copied exactly for the picture of that member. However, if a force is acting on one member but not a second member, in the free body diagram for the second member, it's not going to know directly that that force is acting on the first member. Now, everything's going to be linked together by internal forces, as we'll see, but we're only copying exactly the forces that act only on each individual member in their free body diagram. When we have forces or couples being applied on a junction, or say a pin between our members, we're going to need to choose one member to put that force on, but not the other. And we're going to see that this is going to be cheating a little bit. This is going to still give us the correct external reactions, but the internal reactions are going to be slightly incorrect when we do this. So really, if we have a force acting on a pin in our system that's connecting two or more of our members together, we're probably going to want to use a tactic like we will when we have 3 or more members acting at a junction, which again we'll cover at the end of this section. So these are just the external forces and couples acting on each individual member. Now what's going to be a little bit new is drawing the internal reactions that are happening on all of our objects. So the internal reactions are where 2 or more of our members are being connected together, again at a pin or a peg or a hinge or something like that. What's going to be new here is that in one free body diagram, however we decide to draw those reaction forces and maybe a reaction couple, in the other picture it appears in, it must be acting in the equal but opposite manner. So if we have an internal pin and we draw one member, and at that point we say, okay, if the force from this pin is positive to the right and positive up, in the other diagram where that pin occurs, we are now forced to draw it left and down, so that in the two pictures, that horizontal force is equal and opposite, and the vertical component of force is going to be equal and opposite as well. For external forces, external couples, this is not the case. They get copied exactly the same as they were in every picture that they appear. So it's these internal reactions that must be drawn equal and opposite in typically the 2 free body diagrams in which they appear. Now, each of these free body diagrams we draw is typically going to be a rigid body. So for every free body diagram, we're going to be able to generate 3 equilibrium equations, usually 2 sums of forces and a sum of moment about point in each of these diagrams. Like with trusses or just in general our 2D or even 3D problems, we can generate 3 equations that are going to be true, and mathematically, it's not going to matter what point we take the moment about. However, since we typically do these by hand and we like to make the math easier on ourselves, a rule of thumb that's a little bit more involved than what we saw before is we want to take the moment about points that only appear in one of our free body diagrams. Typically, this is going to make the math a little bit easier. So if we have a choice of a point that only appears in a single free body diagram or a point that's shared between 2 free body diagrams, choose the one that appears in only the one free body diagram to take the moment about. And as we're going through all of our free body diagrams and we're drawing and writing all of our equilibrium equations, numbering them, just like with the truss problems, is going to be really helpful to make sure that we are generating as many linearly independent equations as we have unknowns, so that we're going to know that we do have a solvable system when we're done writing all of our equations. Once we have a linearly independent equations and we have a solvable system, as many Li equations as unknowns, then we can go and solve that linear system of equations. The order we write our equations in, the order we draw our free body diagrams, and the order we solve doesn't matter in the end as long as we have a solvable system of equations. But we're going to see that, again, when solving these by hand, there are some strategies that just make solving steps a little bit easier when we are trying to do this manually.